Thank you for the kind introduction. It is my pleasure today to talk about our work, GLeeFuzz, fuzzing WebGL through error message guided fuzzing, guided mutation, sorry. This is a gleeful collaboration between my wonderful collaborators from Purdue, UC Irvine, and EPFL. So you might have heard about WebGL. WebGL is a framework that released in 2011. It has gone very popular recently. I measured last night, there are, out of the 100 top websites, almost all of them are using WebGL. WebGL enables stunning 3D effects for the web. Apple has used it for advertisement. Google used it for a 3D map. So before we talk about the security characteristic of WebGL, let's see how it works first. So OpenGL is a graphic framework that enables WebGL. WebGL is based on. Let's first have a quick recap on how OpenGL works. So the dashed line separates user space, kernel space, and the hardware. The native app, like a game, which is trusted, want to use the GPU will first link the GL library. Here, the GL library. And it will issue function call into the GL library, and the GL library will issue syscall to the GPU driver. The GPU driver is in the kernel mode. So WebGL content are not trusted. They are downloaded like the rest of a web page just from a random server. We're not going to let the web app directly issue syscall into the GPU driver. That's too dangerous. So major browser vendors like Google, Mozilla, Microsoft, Apple, they all realize there's a security hazard, and here is the solution. So the web app in the red box, the web app is sandboxed. So that it cannot directly issue syscall into the GPU driver. It does not even have the GL libraries. If the web app wants to use WebGL, it will issue an IPC call into the GPU process. And then this GPU process will have a heavy security checks. And then once the WebGL API call passes the security check, it will be forwarded to the GL library, and the GL library will issue syscall to the driver. The WebGL expose low-level graphic libraries and the GPU driver in the kernel mode to attackers. To make it more secure, we want to study and use fuzzing to unreveal vulnerabilities. The fuzzing is a battle-tested technology to find vulnerabilities, so we want to analyze WebGL security through fuzzing. And the state-of-art coverage-guided fuzzing, they use information about what part of the program to execute was executed as a guide to mutation. Let's try, let's try to apply coverage-guided fuzzing on WebGL. So in this strawman solution, ideally the fuzzer will issue random input to the web app, and the web app executes, it will goes into the GPU process and GL libraries, and then we should be able to collect coverage from this browser. Unfortunately, there are many challenges. So we categorize 3 challenges we faced when we developed this strawman solution. And let me talk about these challenges. So the first is collect coverage across processes. First, due to security, web app process is sandboxed. How do we collect coverage information across different processes? And the GPU process the GPU process is in a separate address space. So what makes it worse is some browser and many GL libraries and even the GPU driver are closed sourced. This is our second challenge. Although it is not impossible to re-instrument those binaries, but we cannot find a solution that reliably rewrites all the GL libraries, browser, and the GPU driver. The third challenge is that as we look deeper down the graphic stack, we run into the third problem: how do we collect the coverage information across the user and the kernel boundary? As we were wondering how to effectively fuzz WebGL, we noticed that WebGL has excellent error message feedback. A language like JavaScript are fault tolerant. So because the browser vendors does not want the minor typo or mistake in the code to interfere with user experience. So the browser gives very informative feedback to the user to tell them how to fix the problem. So overall, the workflow of GLeeFuzz is divided into 2 parts. On the left, you have this static analysis part. In this pre-processing step, static analysis is used on the Chrome source code to extract the information that needed for error message guided fuzzing. On the right side is a runtime fuzzing. So the result of static analysis are used at the runtime to perform error message guided mutation. So we categorize the error into two types. For the first type, type 1 error message, it indicates part of the API parameter argument is wrong. So we call this type 1 error message. In this example, the GL buffer data, the first argument, GL alpha, is a type. Right? This one is wrong, and we feed it into the browser will complain about invalid target. The second type 2 error message complain about the WebGL is now in an invalid state. It's not because this specific API call has any problem. It's because the previous call is invalid or missing. So in this case, we did not call the GL use program, and we call the subsequent GL draw array. So there's no program to use. So the browser will complain no valid shader program in use. To avoid this type of error, the WebGL developer must revert the change, revert this line, and add it back. This is an interesting task to build the mutating rule for these two types of error message. So for a web developer who is familiar with WebGL, it is easy for them to decide how to revise the code after reading the error message. However, it is challenging for a computer. In this work, we use static analysis for type 1 error message to find the argument that caused the error, and for type 2 message to find the dependent APIs. To construct a mutating rule for type 1 error message, we need to infer the corporate parameter. And the key idea is that the code that emits the type 1 error message is usually triggered by a check on certain internal variable. So our approach is a backward tent analysis. I will illustrate this idea using an example. So in this example, we have seen the GL buffer data has wrong arguments. The first argument is incorrect. It will pass to this. On the right side, you have the Chrome source code. It will pass all the way down to this function, and this function will emit this error message. And this error message has a check on the switch case on this variable called target. And we use the backward tent analysis to find where this variable comes from. And eventually, we find it comes from here. And this is the GL buffer data API call. And we know the first argument has problem. Similar to type 1 error message, the key idea is that the error-emitting statement depends on certain internal variable. And that variable is updated if this variable is updated by another API. For type 2 error message, we collect this updating API and call them and categorize them into a set. So we identify all those dependencies for each error message and each API. Due to time constraint, I invite you to look at our paper for detail. So generally speaking, error message guided fuzzing has additional benefit compared with traditional code coverage guided feedback. Coverage information alone does not tell us how to mutate. It only tells what input trigger more coverage. So as a result, when the code coverage guided mutation performs random mutation on input, and GLeeFuzz perform meaningful mutation based on error message feedback. Here is the evaluation part of this talk. The evaluation result shows GLeeFuzz beat random mutation. In this diagram, we have GLeeFuzz R, which is a random mutating rule we developed for GL. There's no other baseline that already existing fuzzing engine that perform random mutation on WebGL, so we developed one ourselves. It is showing yellow, and GLeeFuzz is showing blue. On the y-axis, you have how many number of unique WebGL API triggered. On the x-axis is the number of sequence. You can see we beat the random mutation by about 30%. We also measure the number of unique WebGL error message is being triggered. Similarly, we beat the random mutation by 30%. Please refer to our paper for more evaluation results. we find 7 new vulnerabilities through fuzzing, our fuzzing session, including one that caused GPU hang and X server freeze, which basically frees the whole desktop, and another one that has a high severity that is a memory corruption in the GPU process. So in conclusion, fuzzing WebGL interface is hard, and GLeeFuzz, we use error message guided fuzzing to overcome this dependency on code coverage, and we perform meaningful mutation based on error message. We have found 7 new vulnerabilities. So GLeeFuzz is open source. You're welcome to try and let us know if you find any new vulnerabilities. Thank you all. Open to questions.